Now here, what we have, the key ideas. The Born-Haber cycle can be used to calculate the lattice enthalpy that cannot be determined experimentally. This is the purpose of using the Born-Haber cycle. The energy changes that occur in the transformation of the element from the standard state to gaseous state are atomization, ionization, and first electron affinity. So if you remember, these were the different stages which we used to go through. For the metals, you had to calculate the atomization and then ionization. And for the non-metals, you had to calculate the atomization. And what else? What else do we calculate for the non-metals?
Electron affinity.
Electron affinity. Good. So these were the electron affinity. So these were the different enthalpies used to calculate. And we remember that if you had to calculate the second ionization energy of the metal, then you have to add both the first ionization energy and the second ionization energy. And similarly for the electron affinity, but there is a special case for electron affinity that for every non-metal, the first electron affinity is always exothermic. The first electron affinity is exo, and all the rest of the others are high order ionization energies. Second and so on, these are endothermic in nature. But when you try to sum these values, you will always get endothermic for non-metals with electron affinity more than 1. The energy changes, okay. Then we have atomization energies and ionization energies are endothermic changes. It must be specified that they are indicating the uh, they are indicating the atomization and ionization energy. These are always endothermic. Enthalpy of formation and first electron affinity are exothermic changes. Okay, enthalpy of formation can be or cannot be exothermic. It depends. It can it can be positive or it can be negative, but lattice enthalpy is always exothermic. If they say lattice enthalpy, then lattice enthalpy will always be exothermic. It cannot be endothermic. But enthalpy formation can be or cannot be exothermic. Like it means it can be endothermic as well. The first electron affinity in group For electron affinity in group 17 elements is more negative than those of the adjacent group 16 elements. So we used to calculate the electron affinity using the charge density. So according to charge density, if there is greater charge density, then the electron affinity will also be higher. Charge density, the greater the charge density, greater will be the electron affinity. With the exception of the first elements, the first electron affinity decreases as you go down group 16 and 17 because the size decreases. So the electron affinity also decreases. Lattice enthalpies are always exothermic, as mentioned before. Born-Haber cycles can be used to calculate any missing enthalpy value given all the others. So do you remember the formula that we used to calculate the lattice enthalpy for the compounds? What was the formula? In a simple words,
I think it was delta H formation minus, or was it the opposite?
did you not practice any questions of lattice enthalpy again?
The thing is, I'm starting to like forget most chapters, but like that's why I have to solve papers. Like when I solve papers, I revisit them.
Okay, you must revise everything before the paper. Delta HF minus delta H1. This was the formula.
Yeah.
It is a lattice enthalpy of formation. Sorry, this is the lattice enthalpy of just enthalpy of formation. It is enthalpy of formation, and this is H1. Within the H1, we used to have the atomization of metal and ionization of metal, then atomization of non-metal, atomization of the non-metal, plus electron affinity of the non-metal. These were all included in the delta H1. Other theoretical methods used to determine lattice enthalpy may give lower values than the lattice enthalpy. Okay. What about the? Okay, I can go through the other summary table that is from the other book, and from here we can also see the lattice enthalpy formulas. Delta H. Hmm. You have to also remember the enthalpy formula that was used for the compounds in the solutions. The compounds in the solutions had delta H lattice is equal to delta H hydration minus delta H solution. All right. Then lattice enthalpy is the enthalpy change that occurs when one mole of the ionic compound is formed from its gaseous ions under standard conditions. Lattice enthalpy is always negative, as said before. The higher the charges of the ion, the more exothermic the lattice enthalpy. So, because it is related with the charge density, the smaller the ions, the more negative the lattice enthalpy. Then comes the entropy. Entropy is a measure of disorder within a system. The greater the disorder, the higher the entropy. It is represented by the letter delta S. If it is more positive, it means more feasible reaction. The more particles there are in a system, the more disorder and the higher the entropy. Particles with a higher temperature have a higher entropy. Particles move with a greater kinetic energy at high temperatures, and their arrangement becomes more random, so the entropy increases. So you just have to calculate how much disorderness there is, how much there is disorder within the system. The more disorderness there is, the more the entropy. More complicated particles have higher entropy. By more complicated means the more complex formula. The more complex formula of the compound, the higher the entropy. Complex formula. If you can relate with the CaCO3 versus CaO. So, sorry, CaO. So CaCO3 calcium carbonate is more complex than the calcium oxide. The particles in their gaseous state have a high entropy compared to the same particles in their solid or the liquid state. So we do remember that gaseous particles had much higher entropy as compared to the liquid compounds, which have slightly more higher entropy than the solid. Remember that?
Yeah, I do.
Okay, then entropy is measured in joule per calorie per mole. Systems will tend to change to produce an increase in entropy. So it is a natural phenomena that entropy of the systems do increase naturally. A reaction that results in a greater disorder will have a positive entropy. Okay, positive entropy and higher entropy. There is a difference. If they are asking for just as and the value is becoming more positive, it means positive. We would say more entropy. We will just say more entropy. It means that. But if there is delta S and the value of the two entropies is positive, so you will say entropy increases. Entropy increases. It means that entropy increases. A reaction that results in gradient disorder will have a positive entropy. The entropy change when a liquid changes to a gas is much higher than the entropy change when a liquid changes to a liquid, all because of this difference, as I mentioned before, that gases have much higher entropy than the
Sir,
liquid.
wasn't it that it becomes more negative?
No, no, that is for the Gibbs free energy, delta G.
Uh,
Gibbs free energy versus delta G must be negative for a spontaneous reaction, and delta S must be positive for a feasible reaction. These were the requirement for the feasible reaction. Or you could also say spontaneous reaction. The formation of a gas in a reaction will result in an increase in the entropy. The formation of a gas. Okay, the dissolution of the ionic solid results in more freely moving particles being formed and thus an increase in the entropy. Dissolution of solids mean the process of dissolving the ionic compounds in the water to make cations and the anions because they are in the aqueous form. Hydrated ions, we would say then the hydrated ions have more entropy than the solid ionic compound. And then we had a change in entropy fraction is the sum of the entropy of the products minus sum of entropy of the reactants. It is simply the formula delta S is equal to entropy of the products minus entropy of the reactants. Then the feasibility of the reaction determined by the value of the Gibbs free energy. When the value is less than zero, the Gibbs energy is feasible. Simply mean delta G is equal to negative. When we have the value as negative, it means it is a feasible reaction. Delta G is the formula is delta G is equal to delta H minus T delta S. This is the same formula which we applied. And there is another formula which is used in the electrochemistry. Do you know that formula of Gibbs energy related to electrochemical series?
it was negative n f
Hmm.
multiplied by the E naught cell.
Very good. E naught cell. Very good. All right. A system is in equilibrium when delta G is equal to zero. All right. And you can apply the same conditions to find the temperature at which the reaction becomes spontaneous. The temperature at which a change is spontaneous given by T is equal to delta H over delta S. At this temperature, delta G is equal to zero. So they just simply put zero over here and they rearrange the equation to find the value of the delta T. So it became delta H over delta S. Now, summary table from the other source book of the same chapter, it may or may not have different information. Entropy S is the number of the possible arrangements of the particles and the energy in a given system. So we represent S as the possible arrangements of the particles or the energy. A spontaneous change of physical relation involves an increase in total entropy. So we would have delta S to be positive for a spontaneous reaction. If a reaction is not feasible, there is a decrease in entropy, or you would say delta S is negative. So there are two things. There is a decrease in entropy, that means S value is negative. This means decrease entropy. But if delta S is given, it means delta change is negative. Delta S is equal to negative. The entropy increases as substance changes from solid to liquid to a gas or dissolves to form a solution already covered. Our knowledge of the structure and the states of reactant product helps us make us generalization about whether or not the entropy of the reaction is greater than the entropy of the product. So you remember the structure, like for example, the diamond had a very strong structure, so its entropy was very less. Entropy was very higher for that because the particles were strongly bonded there. the entropy change in the system is given by the delta system, product minus reaction. This is the entropy for the system. Gibbs free energy can be calculated using this formula. Now, here is the formula for delta G, and you can also calculate the delta G uh, from the energy changes of the formation, which is delta G of the products minus delta G of the reactants. You can also use this formula if they will provide you the Gibbs free energy of the products and the reactants. On the other hand, this is a formula which you will use when there is the value for the enthalpy and the entropy. A reaction is feasible if the sign of the delta G is negative. The feasibility of the reaction can be predicted using the equation. Okay, now here's the formula which I asked you. If you have to relate with the um, electrochemical series, the electrochemistry or reduction potential. Now definition, there are some tables for the definition as well. The standard enthalpy change of atomization, the enthalpy change when one mole of gaseous atom is formed from the element in standard state under standard condition. And definition of electron affinity, the enthalpy change when one mole of the electron is added to one mole of the gaseous atom from one mole of gaseous ion with a single negative charge under standard condition. It also means uninegative ion. A bond Haber cycle is a type of the enthalpy chain Haber cycle that includes a lattice energy enthalpy chain, the formation and relative relevant electron affinity, enthalpy change of atomization, enthalpy change of ionization. Yanni, you know that I have this whole PDF file which has 32 pages. I might take it longer to read through the whole definition, the whole information. Do you want to read it by yourself?
What?
Do you want to read it by yourself?
Yeah, I'll go through it by myself. Sir, could you send this?
Yeah, I can send you. I can send you the file, and you can tell me which part is not clear to you.
Okay. No,
Because
like I
otherwise,
just wanted to go through the definitions, but you can continue.
okay,
Sir?
yeah, I am
Oh,
sending you the file. The file is being sent to you.
oh okay.
So fine. The about the group two elements as well, we have that one. The thermal stability of the carbonates and nitrates of group two elements depends on the degree to which the group two cation is able to polarize a larger anion. So you remember that we used to calculate the thermal stability of the group 2 carbonates and the nitrates on the basis of the charge density. If there is a smaller cation which has a higher charge density, then it will polarize the anion. We used to calculate the polarization in the anion and we used to calculate the polarizing power of the cation. So cation polarizes the anion. Larger anions are more polarized by the given cation. So if we have if we have two anions and one is larger than the other one, then there will be greater uh, polarization in the larger anion as compared to the smaller anion. Then we have the standard enthalpy change of solution, which is a definition. It is enthalpy change when one mole of the ionic solid dissolves in a sufficient water to form a very dilute solution. That solution may be ectothermic or endothermic. So it all depends upon the bonding within the ionic compound. If the bonding within the ionic compound are much stronger, then it will lead to the formation of endothermic enthalpy. But if the ionic compound is more easily dissolved, it will be exothermic. And we used to calculate the value, the enthalpy of the solution from the difference of the enthalpies of the other two substances. The enthalpy change of hydration is enthalpy change when one mole of gaseous ions dissolve in sufficient water. So there's a difference between the enthalpy of solution and hydration. In enthalpy solution, we have the ionic solid dissolved, and in hydration, we have the gaseous ions dissolved. To form a very dilute solution, delta H hydration is always exothermic. So here is also another difference. For the solution, it could be exothermic or endothermic, and for the hydration, it is always exothermic. As law can be applied to construct energy cycle, determine enthalpy change of solution and enthalpy of hydration. The decrease in solubility group to sulfate down the group can be explained in terms of the relative values of the enthalpy change of hydration and corresponding lattice enthalpy. All right. Now, if you remember, we used to tell why the sulfate used the solubility of the sulfates used to decrease going down the group. So we used to say the difference was on the basis of the enthalpy of the solution versus enthalpy of the hydration. If I make it clear to solubility of the hydroxides, maybe it will be mentioned somewhere here in group 2. Okay. So solubility of the hydroxides, it used to increase going down the group, hydroxides. It was because the decrease in lattice enthalpy of in the lattice enthalpy was greater than decrease in enthalpy of solution. The, de- the decrease in lattice enthalpy was greater than the decrease in the enthalpy of the solution for the hydroxides. This was the reason behind the increase in the solubility of the hydroxides. And then with respect to the decrease in solubility of sulfates, it was because the decrease in enthalpy of solution, the decrease in enthalpy of solution was greater than the decrease in enthalpy of lattice enthalpy. There was much greater decrease in enthalpy of solution for the sulfates as compared to the lattice enthalpy. Is that clear?
Yeah, it is.
Okay, then experimentally derived lattice energies can be found using one. Okay, these are all almost same things. The sulfate group to sulfate decrease with the increasing proton number. This is because the enthalpy change solution becomes increasingly unfavorable. The reverse effect is shown by the group to hydroxide. So they have just mentioned this much information related to the solubility of the sulfates versus hydroxides. Definitions can be covered from these table as well. If you want to go through, you can also go to the definitions table from here. Then comes the second chapter, electrochemistry. So you receive the file now? No, it's not sent. Let me check it again. Why it's not sent? Just give me a minute. It's sending. Okay, it's sent now. Check your WhatsApp. Got the file? Yani, have you got the file?
Yeah, I did.
Okay. Now about the electrochemistry, a half cell is made when a metal is placed in a solution of its ion and a redox equilibrium is set up. The buildup of electrons on the metal produces an electrode potential between the metal and electrode and solution. So these are all the processes occurring within the electrochemical reaction. It is not possible to measure the potential of a half cell, only its potential difference against another half cell is measured. When two half cells are connected, an electrochemical cell is produced. A salt bridge is needed to connect the cells and is used to balance the charges of the cell. Basically, the salt bridge contains the inert ionic compound solution that is used to maintain the electrical neutrality between the two half cells by moving their ions on the opposite charges. When two half cells are connected, an electrochemical cell is produced. A salt bridge. Okay. Standard electropotentials are measured against standard using hydrogen gas with a platinum electrode, which is given E naught is equal to 0.04. The standard conditions are 1 mole per dm2 concentration of ions in solutions and 298 Kelvin and 101 kilopascal. If there is no solid metal in the half cell, platinum or graphite electrodes are. We had to select const, the composition of the electrode. It could be a metal, it could not be a metal. There was only two different cases, metal or the platinum or graphite electrode. You have to go through the diagrams in which there were different combinations of the half cells with the SHE. There you will find when they use a metal as electrode and when they use a platinum or graphite as an electrode. The more positive the standard potential, the more the reduction reaction is favored. The more negative the standard potential, the more the oxidation is favored. A list of reduction electropotentials follows the electrochemical series. Uh, the half equations are always written as reduction reaction in the forward direction. This is the electrochemical series they are referring to. This series will not be given to you as a whole separate list in the CA exam. Instead, you will be only provided with the relevant equations within the question which you need to use. Nothing as a separate list will be given. Then key ideas, when two half cells are combined to form an electrochemical cell, the cell with the more positive potential is placed on the left. So their reduction occurs. And the oxidation occurs in the cell with the least positive potential and it is placed on the right. So that's why the formula used to be E cell is E cathode minus E anode or E reduction minus E oxidation. The negative electrode is the anode and the oxidation takes place here. Negative electrode is the anode. It is negative because there is a loss of electron at the anode. That's why it is negatively charged. The positive electrode is a cathode and reduction takes place here. Standard electropotential from the electrochemical series can be used to calculate the standard cell potential of the electrochemical series. And this is the formula to find the to find the E naught of the cell. Electrons will follow from the more negative electron, which is the anode, where oxidation occurs, to the more positive electron, where the reduction occurs. So it means electron flow will be from anode to cathode. It is in the internal circuit, anode to cathode. It is through the external circuit, not through the internal. It's through the external circuit. If inert cell is positive, the reaction is feasible. So we have used the values of the delta G, delta S, and delta E, or just inert cell, to determine whether the reaction is feasible or not. Not all cell feasible reactions will occur because the reaction may have a high activation energy. Now, this is something different. Uh, we do use the inert cell to check whether the reaction is feasible or not. But at the same time, we need to see what about the activation energy, because some reactions have a very high activation energy and it becomes so slow that it does not appear to be happening. We can use electropotentials to work out the oxidizing power of the halogens. This is all the same concept we have been using. And all these topics require one simple concept, that the substance with the more standard electropotential will get reduced. The concentration of the solution affects the electropotential cell. The concentration are not 1 mole per dm cube. So yeah, this is the topic where we said that what is the effect of the concentration of the ion on the electropotential. The electropotential at a non-standard concentration can be calculated using the Nernst equation. This is the Nernst equation. E is equal to E naught plus 0.059 over Z. Z is what? Do you remember the Z? What is Z here?
What?
What is Z here?
Wait, I forgot.
Number of electrons involved in the chemical reaction.
Hmm.
If there is just one chemical equation, then you have to see how many electrons are involved. And when there are two chemical reactions, then you have to balance the both equations. And during balancing, you will see the number of electron lost will be equivalent to number of electron gain. So electron lost will be equivalent to the electrons gained. Those electrons will be used here in the Z, and then this formula. In electrolysis, the electrical energy is transferred to chemical energy using the cell or the battery. In molten liquid, the ions and the electrolyte are discharged at each respective electrode. The ions are discharged at the cathode and ions are discharged at the anode. Direct current is needed for electrolysis to work. Now, this is a different type of the cell in which the current is used to make the chemical reaction work. In the electrolysis of aqueous solution, the hydrogen ions and hydroxide ions in the electrolyte are attracted to their respective oppositely charged electrode. The electrochemical series can be used to determine which ions are discharged at each electrode. So, if you remember, the electrolysis of the aqueous solution was slightly complicated as compared to the electrolysis of the molten ions. At the cathode, ions with an electron potential higher than a hydrogen will be discharged. Now, I would say that do not say, uh, you just say the value is more positive. If the value of the substance is more positive, electron potential is more positive than the hydrogen as compared to hydrogen, then that substance will be reduced. Hydrogen ion will not be reduced in that situation. At the anode, halide ions are preferentially discharged compared to hydroxide ions. Otherwise, hydroxide ions are discharged and oxygen gas is formed. Now, there was the concept of the concentration. What's Whichever ion is in more concentration, that will be discharged. If hydroxide ions have more concentration, if they are more concentrated, hydroxide are more. I would say if hydroxide ions are in more amount of hydroxide ions, this is possible in case of the dilute solution. So if you use a dilute solution of the ionic compound, then hydroxide ion will be discharged. But if you use the concentrated solution of the ionic compound, and that ionic compound could contain either the chloride, bromide, or iodide, then they will be discharged instead of the hydroxide ion. Are you getting the point?
Kind of. Sir, wasn't there like a rule where it was like zinc and iron would, I don't
I'm
know.
uh, I'm saying about the anions over here. These are
Oh,
all anions, not the cations. So with respect to the anions, if they are in more amount in the concentrated situation, then they will be discharged. The chloride, bromide, and iodide, they will be discharged, not the hydroxide ion. And the other part is of cations, you're right. It will include lead, zinc, and the iron. If they are concentrated on the G3 ions, if they are in the concentrated form, then they will be discharged, not the hydrogen ion. Even though that all these three cations have less positive reduction potential as compared to the hydrogen. They all have the less positive reduction potential. But when used a concentrated solution, then these three will be discharged: lead, zinc, and iron. All right.
yeah.
And the same part which I have just explained before about the hydroxide ion versus the halide ion. This is what they have mentioned. Very dilute concentration of the halide ions will enable hydroxide ions to be discharged to make the oxygen gas. So at dilute solutions, the amount of the halide ion becomes lower. They become lower than the hydroxide ion. They become lower in amount as compared to hydroxide ion. And then we have the formula to calculate the amount of the substance produced. So I gave you the formula. I told you the formula. This is a simple formula which you just need amount. We would say on electrode. Amount on electrode. It could be a solid or it could be a gaseous. If it is solid, then you determine the mass, and if it is gas, then you determine the volume. So the formula was I into T. I is current in ampere, T is time in second, divided by N, number of moles. I would say Ne negative, that means number of moles of electron, multiplied by F. F is Faraday, 96500, into,
AR,
into,
right?
if it is solid, then AR. If it is solid, like if it is one atom, then you put AR. But if it is a gas, then you put molar volume. And molar volume must be properly indicated. It could be 24 dmq if it is room temperature and pressure or standard condition, or it could be 22.4 dmq if it is STP. At STP, it should be clearly indicated STP. STP means you don't need to know that STP, because there is a very confusion over here. STP have full form of standard temperature and pressure, but at the same time, when they write standard temperature pressure, then they use 24 dmq. It's totally confusing. So you just need to see if they clearly write STP, then write 22.4 dmq. And all the other conditions, you will write 24 dmq, including the room temperature word or RTP or standard condition. If they write completely standard condition, then use 24 dmq. Clear?
Yeah.
Then during electrolysis, reduction occurs at the cathode. Is the Okay, one more thing. Don't look at the negative wording because they are relating with the other type of the cell which we are not discussing right now. We are only taking the half cell having the sound break. But yes, it is correct that sorry, over here. So it is correct that the reduction occurs at the cathode and the oxidation occurs at the anode. Metal is formed at the cathode and the non-metal is formed at non-metal is formed at the anode, which is mostly gaseous state. Hydrogen may be formed at the cathode and oxygen at the anode when dilute aqueous solution the metal sounds are electrolyzed. Okay, then we have the formula already covered this part. Standard condition. What are the standard condition? It is must be 101 kilopascal and 1 mole per meter cube. Do you remember the construction of the SHE? Do you clearly remember SHE construction?
I remember the SHE. Yeah.
You have to properly remember all the labels in present there.
Oh yeah, yeah.
And then standard electric pressure of the house is the voltage the house under standard conditions compared with the standard hydrogen electrode that's already covered. The direction of the flow of electrons also covered, the mass equation covered. They are more or less same things because I have used summary tables from all the three resource books. So these are just some summarized values. Then equilibrium, strong acids completely dissociate in dilute solution in water, whereas weak acid partially dissociate. This is the definition between the this is the definition for the weak and the strong acid. This then the formula for the any acid pH is minus log of hydrogen ion. The strength of the weak acid determined by the value of the dissociation of acid dissociation constant Ka. The larger the Ka, the stronger the acid. Then Kw formula is hydrogen ion to hydroxide ion and for pure water. The concentration of the hydrogen ion and hydroxide ion are equal, or you could write Kw is equal to K of the hydrogen ions. The pH of your water decreases with the increase in temperature. So yes, we did relate with the temperature how it used to decrease. The pH could use to decrease with the increased temperature, but even then the water was clear. So the water was distilled. Or you could say the water remains neutral. The water remains neutral even at a lower pH because it was related with the concentration of the hydrogen ions. Then buffer solution, there were two buffer solution. The acid buffers contain a weak acid mixed with the salt with a weak acid. This is the acid buffer, and the other one is the basic buffer in which uh, there is a weak base mixed with the salt of the weak base. Buffer releases the small changes in the pH. The pH of the buffer changes slightly on adding acid or base. The pH of the acidic buffer can be calculated using the equation. So this was the formula pH is equal to pK plus log of salt over acid or conjugate base over weak acid. Do remember that they are using only one formula, although there is the other formula in which they do not use the pKa. They just write hydrogen. They just write Ka. This one. This is the other formula. It's up to you whether you want to use this formula or you want to use this formula. You have both choice because they are same. All right.
Yeah.
Okay, then the solubility and the product equilibrium constant KSP only applies to saturated solutions or sparingly soluble solid. KSP is applied only for the sparingly soluble solid. KSP, the product of the concentration of the ions formed raised to the power of the constitutive moles. Now, if you remember, we used to calculate the KSP. So, if I just put a very simple example in which we have the I would say AB2. This is an ionic compound AB2 and it dissociates into its respective ions like this. Then we will have 1 mole of the A positive ions and 2 moles of the B negative ions like this. But when you will write on its KSP formula, it will be written as KSP is equal to concentration of the A multiplied by concentration of the B, but the same amount must be used. It will be two. It remains the same amount. 2B negative. I'm writing deliberately 2 over here because to make it clear that the concentration does not change. And at the same time, this 2 becomes forward. So it will be written like this. So for every uh, partially stable compound, the concentration of A negative, the cations are equal to the B negative, which means I can put I can put both of them as x over here and x over here, which means if KSP must be calculated, then it can be written like x into 2x square. This will become, sorry, 2x whole square, 2x whole square. This will become 4x cube. So if you have to calculate the solubility, if they clearly say solubility, if you have to find the solubility amount, then it means you have to find the value of x. KSP is equal to 4x cube. You can just go through the multiple examples which were already done in the literature. And then if a soluble solid and an insoluble solid containing a common ion are mixed together, the insoluble solid will precipitate out more easily because the equilibrium shifts to favor its formation. This is the common ion effect. So this was a common ion effect to precipitate out the less soluble or the partially soluble compound by using the same ion that was present in the both compound. Then partition coefficient, it is the amount of the solute dissolved in the two immiscible solvent. One is it could be written something like this. In the numerator, do remember this formula that in the numerator it could be organic solvent or it could be less, it could be organic solvent or it could be less polar. Whereas in the numerator, it could be the water or more polar solvent. We had one of these two cases. You will be using your previous knowledge to decide which solvent could be considered to be more polar or less polar. Or to make it simple, they can give you one solvent as a water, and the other solvent will definitely be the organic compound. That will be more easier. So use this formula, the concentration of the solute in the organic, let's suppose, divided by the concentration of the solute in the water solvent. And you can see that if the KPC value is greater than 1, then it means that the solute is dissolved more in the numerator solvent. Whatsoever is written, it will dissolve more in the solvent which is in the numerator. If it is organic, then you will write organic. And if the value is less than 1, it means the solute is more dissolved in the solvent mentioned in the denominator. It could be aqueous or it could be less or more polar solvent. Is that clear? Yeah, is that clear? Are you there? Yani, are you there?
I am.
You are not responding. Are you even listening or you are reading by yourself?
No, I'm listening.
You are not responding.
Sorry, I didn't hear you.
Okay, the last chapter, direction kinetics. Uh, so for the reaction kinetics, the rate equation describes the relationship between the rate of the reaction, the rate constant, and the concentration of the reactants in a given reaction. So this is the formula. Rate is equal to K into multiplied by the concentration of one reactant, which means the order of that reactant multiplied by the order of the second reactant if they are two reactants, and they are all calculated experimentally. There is no direct relation with the stipulated, rather there is a relation with the mechanism of the reaction as well. So what we say about the order of the reaction are the powers to which the concentrations are raised, to which the concentration are raised in the rate equation. The overall order of the reaction is the sum of the powers of the concentration. So if you just add up m and n, this will give you the overall order of the reaction. The units of the rate constant depend on the order of the reaction. So you have retained the equation according to the order of the reaction, and that will give you the units. The unit for the rate are always mole per dm³ per second. This is for the rate of the reaction. An order of the reaction can be determined by monitoring the concentration of the reactant over time, plot a graph of concentration against time, and then rate against concentration. You should remember there were three different graphs to calculate the order of the reaction. The graph between the concentration versus time, and the other graph was the concentration versus rate. So you have all the literature, and you must be familiar with those graphs. The gradient of a concentration against time gives the rate of the reaction. So if you have the graph between the concentration and the time, then simply determine the gradient. The half-life is the time. Now the order of the reaction could also be checked from the half-life. So if the half-life remains constant, then it means the reaction is a first order. The half-life remains constant for the first order reaction. But if the half-life decreases, then it indicates a zero order reaction. On the other hand, if the half-life increases with the passage of time, it will indicate a second order. If the initial rate increases by the same factor as the concentration of the reactant, then the reaction is first order with respect to that reactant. So initial rate increases by the same factor. So there was a table used to calculate the order of the reaction by using the values from the table. You used to keep one reactant constant and the other you have to keep one reactant to be varying, whereas the other reactant used to be constant to find the order of the reaction with respect to that particular reactant. A rate constant can be calculated by substituting the values from the data about the concentration of the reactants and initial rates. Determine the order of the reaction first, then substitute the value into the derived rate equation. The rate constant can also be determined from the half-life and initial concentration of the reactant. For a first order reaction K, 0.69 give a half-life. This is the value is used if you have to relate between the rate constant and the half-life. To monitor the concentration of the reactant over time, the reaction needs to be stopped in the sample mixture. This can be difficult to achieve. Ice is often used to slow the reaction down. Methods to monitor the progress of the reaction must be selected based on the features of the reaction. For example, measuring the volume of the gas product over time, if only one gas is produced, or using a light sensor if precipitate is produced. These are the different methods or the instruments used to find the order or to find the progress of the reaction, because if you know the progress of the reaction, then you can find the order of the reaction. And then moving forward, elementary reactions consist of a single step. The order of elementary reactions is given by the number of the moles of each reaction. This is about the mechanism of the reaction. A rate equation must be determined experimentally. The flow step of the reaction mechanism is the rate determining step. The rate equation includes reactants in and before the rate determining step. So you have practiced the uh, mechanism reaction as well. Each in a reaction mechanism must be an elementary reaction. The number of the moles of the reactions in and before the rate determined step is equal to the order of the reaction with respect to that reaction. So you have to remember that the moles of the reaction in and before the rate determined step. That means if any fast step is there before the rate determined step, you will include that reaction in the overall order of the reaction or overall rate equation. We can use the rate equation and stoichiometric equation to verify reaction mechanism. We can also use reaction mechanism to reduce the order of the reaction by considering the number of the moles of the reactants in and before the rate determinant step. Then catalysts, there were two different catalysts, the heterogeneous and homogeneous catalysts. Heterogeneous catalysts are in a different phase to the reactants. It means they are in different physical state. They adsorb the reactant molecules, holding them and weakening the bonds to lower the activation energy. The products dissolve from the catalyst surface. Example of hydrogen catalysts include iron in the Haber process and platinum, and protein in the catalytic converters. Homogeneous catalysts are in the same phase as the reactant. They form intermediate which reduce activation energy for the reaction. Many are transition metal compounds because they can rapidly change oxidation states. Example of homogeneous catalysts include iron or iron plus 2 or iron 3 plus ion in the reaction between the sodium thiosulfate, the thiosulfate ion and the iodide ions, and nitrogen dioxide is the oxidation of sulfur dioxide. So I have discovered the summarized information of this chapter as well. There are two more tables. There will be more or less similar information given in these tables, which I think you can also go through. All right.
Okay.
So this was all the physical part of the chemistry which I have covered. So
Thank
now,
you, sir.
yeah.
Thank you for the revision.
I know it was fast because you know that there's a lot of information already there in the summarized information, and if I make it slow, then the class will be of like more longer time. It will be of no use unless you read by yourself because
Yeah.
you have to learn the equations, you have to learn the formula and the concept. So all the concepts are there in this summarized or the vision note of the whole A2. Okay.
Yeah. Okay.
So I would recommend you to go through the whole PDF, and after properly understanding each and every part from all the tables, you must start with practicing the past papers. Try to attempt at least 2 to 3 papers as a practice, and then go with the mock exam. Like mock exam is the one in which you will time yourself with of 2 hours, exactly 2 hours,
Yeah.
and you will after completing the 2 hours you have to mark your paper accordingly and give me the grade you got in that paper from the threshold. I need at least one result of such a mock exam.
Okay.
All right, so I hope this was our last class today, because from tomorrow onward we will have the weekdays starting here. So it was a nice journey with you for this whole session, starting from the July